Oh, by George, Holmes, what a romantic sight. Niagara Falls by moonlight. Yes, indeed, quite breathtaking. Hey, what the deuce was that? Just some ducks quacking, Watson. Relax and enjoy the view. Yes, but I say, isn't it a bit dangerous standing right on the edge of the falls in the middle of the night? I mean, what if Moriarty... Don't worry about that bird brain, Watson. I'm much too clever to fall for any of his tricks.
Those two flatfoots are going to fall a lot further than they think.
What the blaze it? Oh, good grief, it's Moriarty.
I knew I'd triumph in the end. If you two are so fond of Niagara Falls, now's your chance to get a really good close-up view.
But you can't push us over the falls just like that. It's simply not cricket. No, it's just not done, old chap.
Isn't it? Well, how should I push you over then?
In a barrel, of course. That's the proper way.
Ah, good idea. Oh, what am I saying? I left my barrel 40 kilometers upstream. Oh, I know. I'll tie you two up against this tree, then I'll canoe up the river to fetch the barrel. After all, there's plenty of time. I've got all night.
I wouldn't be so sure, Moriarty. The current in this river runs at 6 kilometers per hour. It's now just about midnight, and the park ranger comes on duty shortly after 5 a.m., so he'll rescue us before you can get back.
Curses, could Holmes be right? Let me see. I have 5 hours to go 40 kilometers against the current and 40 kilometers with the current. So how fast must I go? Yes. I must average 8 kilometers an hour over the whole trip. But that's exactly the speed of my motorized canoe. I'll be back before the park ranger gets here. No problem. Then you two will really be for the high jump.
Are you quite sure Moriarty can't make it back in 5 hours, Holmes? Absolutely certain. Instead, it'll take him nearly 23 hours to do the round trip. You're certain? Yes. In fact, and here comes the clue, Watson, I'll bet you a bill of any denomination that I'm right.
Welcome to the 9th program in the Power of Algebra series. In the previous program, we continued the exploration of factoring and saw how what appears to be a quite complicated equation can be simplified by looking for the common factor, which in this case is 4. In this program, we're going to see how to simplify algebraic expressions that involve fractions. Algebraic fractions are no more difficult to do than any other fractions. Exactly the same rules apply whether you're talking about 3/8 or x over y. You still have a numerator on top and a denominator on the bottom. But beware of unknowns in the denominator. You can't divide by 0. You can reduce a more complicated-looking arithmetic fraction to its lowest terms by looking for the factor common to the numerator and the denominator. Here it's 7. When you have a more complicated-looking algebraic fraction, you can use the same technique. In this case, the common factors are 3, x, and y. So, the fraction can be reduced to 2x over 3. Here's one that looks even trickier, but works in exactly the same way. Only here, in order to see what the common factor is, we have to first factor the top and bottom into binomials. X minus 1 square becomes x minus 1 times x minus 1. And x squared minus 9x plus 8 becomes x minus 1 times x minus 8. Now it's easy to see that the common factor is x minus 1, which allows us to reduce the original fraction to something much simpler. If factoring works the same way for fractions in algebra as it does for fractions in arithmetic, so do all the basic operations. When you multiply 3/8 by 5/7, you first multiply the two numerators to get 15, and then multiply the two denominators to get 56. So when you multiply a over b by c over d, you first multiply a times c, then b times d to get ac over bd. The same goes for division. If you have to divide 3/8 by 5/7, you replace the divisor, 5/7, by its reciprocal. In other words, you turn it upside down and multiply by 7/5 to get 21/40. And that's exactly what you do in algebra. If you have to divide a over b by c over d, you replace the divisor by its reciprocal and multiply by d over c to get ad over bc. That's easy for multiplication and division. Unfortunately, it's not quite so straightforward for addition and subtraction. I need to get this straight because I've got to figure out how long it would take me to fill this pool if I didn't have a fill pipe. And instead, I had to just do it with this garden hose.
My name is Orville Baker. I'm a technician here at WLPB. I just received my BS degree in physics here at Southern University in Baton Rouge. Algebra is important to all mathematics, and regardless of what type of mathematics that you do, algebra is always the road traveled in order to get the end result you're trying to find in any mathematical endeavor. And in physics in particular, no matter how complex the equation is, you always have to use algebra to find the solution. Mathematics, and particularly algebra, is the language of science. In fact, it would be almost safe to say that any physicist that is competent is also a very competent mathematician. If you expect to survive in the next century, you're going to have a background in mathematics, because our technology, our job force, our job descriptions are changing more and more to mathematically inclined understanding. If you're going to deal with the computers, if you're going to deal even with car manufacturing, you have to understand the difference between metric and English system and be able to make those conversions using mathematics, using algebra. Those who will survive the next century, those who have the jobs, and those who have a better standard of living, with those who are not afraid to look at math and tackle it.
I said that adding and subtracting algebraic fractions isn't quite as straightforward as multiplying and dividing them. The big difference is that when you're multiplying any fractions, you can multiply both the numerators and the denominators. When it comes to addition, you can only add the numerators if both of the denominators are the same. In other words, you can only add fractions if they have a common denominator. Here's a very simple example. Add 2/9 and 5/9. You add the numerators and keep the same denominator to get 2 plus 5 over 9, or 7/9. It's the same when adding algebraic fractions. When you add a over c and b over c, you get a plus b over c. The identical process takes place with subtraction. But you can only do that if the two fractions that you're adding or subtracting have got a common denominator. What if they don't? What if you're faced with adding, say, 3/7 and 2/5? How do you take those two different denominators and turn them into a common denominator? Well, we look for the least common denominator, the smallest multiple of 7 and 5, which is 35. And to change these two denominators into 35, we multiply both terms in the first fraction by 5 and both terms in the second fraction by 7, which gives us 15/35 plus 14/35. Now we can add these fractions to get 29/35. We use precisely the same technique to add algebraic fractions with unlike denominators, as here. The least common denominator, LCD, in this case is 12x. To change the two unlike denominators into 12x, we multiply both terms in the first fraction by 4 and both terms in the second fraction by 3, which gives us 20 over 12x plus 27 over 12x. Then we add the two fractions to give us 47 over 12x. So once you understand how the least common denominator process works for adding and subtracting fractions in arithmetic, you'll also know how it works in algebra. Which brings me back to the swimming pool problem. How long would it take to fill this pool if I didn't have that fill pipe? And instead I had to do it with just the garden hose. Well, with the fill pipe running alone, it takes it 5 hours to fill the pool. With both the fill pipe and the hose running, it only takes 3 hours. So I take the formula for rate of work, which is rate equals work divided by time. Now, the work to be done is to fill one pool, so work equals 1. And since the fill pipe takes 5 hours to fill the pool, we can say that its rate is 1 over 5. But since the hose's rate is unknown, we can only say it's 1 over x hours. In other words, the total rate is 1 over 5 plus 1 over x. And since this combined rate fills the pool in 3 hours, our time here is 3. Now, if we rearrange all this into the equation for work, which is work equals rate multiplied by time, we get this. And if we multiply that out, we get 1 equals 3 over 5 plus 3 over x. The least common denominator here is 5x. Since we're working with an equation, we keep it balanced by multiplying both sides by 5x. And we end up with 5x equals 3x plus 15, or 2x equals 15, or x equals 7.5. So, I've been able to figure out that should this fill pipe ever be out of action, I'll be able to fill the pool with this garden hose in 7.5 hours. All thanks to knowing about the least common denominator. Holmes and Watson should thank their lucky stars that Moriarty didn't have access to the same information.
I wish we knew the time, Holmes, but I can't get it. My pocket watch. Look at the sun, man. It's just coming over the horizon. The sun rises just after 5 a.m. today, and still no sign of Moriarty. Then right on cue, here comes the park ranger to set us free. Thank you, Ranger. Now we can take a leisurely stroll along the river. Moriarty won't make it back until just before 11 o'clock tonight. Oh, what an intellect! But what was the clue this time? Something to do with denomination? Least common denominator. Do I have to spell everything out for you? L, C, D. But what exactly did Moriarty do wrong? Well, what did he want to calculate? How fast his canoe should go to get from the top of the falls, point A, 40 kilometers upstream, to where his barrel was at point B, and back again, facing a current as he goes upstream of 6 kilometers per hour. Don't forget that. Yes, and having to complete the round trip between midnight and 5 a.m., a total time of 5 hours. So the equation we want here is time equals distance divided by rate. Right. The time is 5 hours. The distance is 40 kilometers upstream, divided by the rate, which is our unknown x, minus the current, which is 6 kilometers an hour, because the current would be going against Moriarty. And then we add to that the distance downstream, which is also 40 kilometers, divided by x, plus the current of 6 kilometers an hour, because now Moriarty would have the current going with him. But I say you can't add those two fractions because they have unlike denominators. Oh, I see it all now. We have to look for the least common denominator, which is very simple here. The smallest multiple of x minus 6 and x plus 6 is x minus 6 times x plus 6. So we multiply everything in the equation by that. So the whole thing multiplies out to this, and then this, and then this, which we change into the standard form for a quadratic equation, then simplify by factoring out the 5, and then factor that into 2 binomials, revealing that the 2 possible values of x are -2, which is impossible, or +18. Which tells us that the speed at which Moriarty should have gone to make the round trip was 18 kilometers per hour, not 8 kilometers per hour. Well, then how did Moriarty arrive at that incorrect answer? Because instead of looking for the least common denominator, he not only added the numerators, but he also tried to add the unlike denominators. Then he simplified that to get 40 over x, which gives x a value of 8. No wonder you said the round trip would take nearly 23 hours.
Ha! Call me a bird brain, would they? I'll give them birds on the brain.
Get away, you nasty things. Shoot! Shoot! Oh, I say.